Hello, my name is Tubas and I would like to talk about our virtual project. I would like to start off by talking about the purpose of our project. We aimed to program a robotic arm to take items from its own conveyor and sort those items in a pallet with a fixed size. Our program has database, a user interface, and a business logic part. In our database, we can store the sizes of items which are going to be sorted in a pallet. And in our business logic, we program the algorithms and the logic of how those items are going to be sorted. In our graphical user interface, we have buttons and fields which users can interact with and take items from the database, enter new items to the database, and observe the flow of items in the system. To be able to achieve that, we have used Dobo Magician Arm. Dobo Magician Arm can rotate 180 degrees and it can go up and down 85 degrees. We have used Dobo Magician Arm's its own API, which made things a bit easier for us. The general language used to code and program our robotic arm was Python. Dobo Magician Arm comes with its own compiler and API menu. We have used that to test and design our system.
These requirements describe the functional and non-functional part of the system. The functional requirements describe what functions the system must have, and the non-functional, how this should be achieved. Functional requirements are given in the form of so-called user stories that are written from the perspective of the end user. As a system operator, I would like to enter new items into the database. As a system operator, I would like to specify the sizes of that package. As a system operator, I would like to specify the details of how the package should be sorted. As a system operator, I would like to delete and update data. As a user, I would like to get statistical data on quantities of packages to be processed and available in the system. As a user, I would like to activate and deactivate the system. Since there will not be a lot of users, our suggestion is making a screen with key functionalities, such as inserting data, start-stop operations, and shutting down specific units. Also, there will be a screen for tracking the statistical data for the specific machine, such as orders per unit of time, power consumption, and so on. The data insertion will be done by a specialist who can use the login option on one of the machines, and there she will be prompted to a menu. For this system, two key types of devices will be needed. A robot arm, in our case the Dobo Magician, referred to as robot arm, which is a multifunctional desktop robotic arm for practical training education. Installed with different end tools, Dobo Magician can be utilized to have functions such as 3D printing, laser engraving, writing, and drawing. Software interfaces. The software interface for the arm will be Dobo Magician's firmware. The server will have a connection to an SQL database where all completed and non-completed orders will be stored. The server will keep track of these orders and will assign a new order to each machine.
Let's take a look how the items are sorted in our system, how the logic is designed in our system. The position where x-axis and y-axis meet each other on the left corner is assigned to be 000 position in Dobo Magician. We start putting items there first. The items are going to be positioned in x-axis first, next to each other. Our system is checking how much space is left after positioning each item If there will be no space left in X or Y or Z axis, it's going to stop. While putting the items in the X axis, positioning them next to each other, if there will be no space left, next item is going to be positioned up in the Z axis. And it's going to keep moving in Z axis and X axis until the row is completely finished. After one row is finished and there are no space left, our system is going to move in the Y axis up, and it's going to start positioning to the 0, 0, 0 position again. First in X axis, then in Z axis, and it's going to move up again until the task defined in the database is over. Let's take a look how the items are sorted in our system, how the logic is designed in our system. The position where X-axis and Y-axis meet each other on the left corner is assigned to be 0, 0, 0 position in Double Magician. We start putting items there first. The items are going to be positioned in X-axis first, next to each other. Our system is checking how much space is left after positioning each item. If there will be no space left in X or Y or Z axis, it's going to stop. While putting the items in the X axis, positioning them next to each other, if there will be no space left, next item is going to be positioned up in the Z axis. And it's going to keep moving in Z axis and X axis until the row is completely finished. After one row is finished and there are no space left, our system is going to move in the Y axis up, and it's going to start positioning to the 0, 0, 0 position again. First in X axis, then in Z axis, and it's going to move up again until the task defined in the database is over.
The database is implemented in PostgreSQL. This was chosen because of the availability of add-ons in standard programming software. Besides Boolean, it is not using any terms that are version specific, and in many other versions Boolean is also used. Therefore, the same code for table creation can potentially be used using a different piece of SQL software. The first table that was implemented is OPATS, short for operator account. This table contains the login data for the database operator. And this table has no relation to the other tables. The next table is box info. It contains all the data for the boxes, which determines the dimensions of the box and the parameters on how the box will be sorted on the pallet. The box info table also contains the box ID, which relates to package info, where it is used as a foreign key and it is the primary key of the table. The package info table has a pallet ID and a num, which is auto-incremented variable, and a primary key, number of boxes, number of repetitions, meaning pallets in a package, time, date of shipment, and Boolean code completed. It has a no action attribute if the foreign key is changed, which means that if the foreign key is removed, there won't be any action taken by the system, and it will keep the same foreign key. The shipped pallet table stores data received from the customer and stores information that may be necessary to customers, such as broken boxes field, which is holding the data of defected boxes or boxes with broken items in the delivery. Since the client for the customer is out of scope for the project, the data will be hard-coded. This table is meant to contain statistical data. The database implementation doesn't end with the database script itself. It also needs Python code to make it insertable through a Python-based environment. The database connector is implemented with the use of SciSOP. This allows Python to establish a connection with a PostgreSQL database and do queries on it. The code snippet shows how the connection to the database is established. It calls the method to connect and gives the respective data such as database name, IP address, port, user, and password. This snippet shows how the SQL query is defined in Python. The query is done in the form of string, and a method by the name of execute is called. For backend implementation, the functionality of the robot utilizes a DLL library which gives basic API in other coding environments besides Dubot Studio. The team used Visual Studio as EDA. This DLL, however, doesn't contain functionality for the infrared sensor which normally works in Dubot Studio, and the team has proved that the functionality should be able to work normally but doesn't in the specific environments outside Dubot Studio. Most backend variables are declared as global, which means that they can be accessed from anywhere in the system. Initially, these variables are hard-coded to represent the low boundaries of the palette. They are then updated with the respective data extracted from the database with the function callback database info. Current boxes keeps track of how many boxes are there on the palette, and target boxes is a variable that keeps track of how many boxes there should be in a palette total. The move function is a function responsible for the movement of the robot. It utilizes the Dubot API functionality such as starting the conveyor and stopping it, moving the arm in respective positions and picking up the box. The function first activates the conveyor belt, then the infrared sensor. Then there is a check with an if clause where the function checks if the infrared has sensed anything. Then the conveyor stops. After that, the arm will reach out and pick up the box and put it down onto the pallet. After that, there are multiple if-else clauses used for calculating the next coordinates. Another function that is a core for the operation of the Dubot is callback database info. This function utilizes most of the same global variables as move function. Here, most variables are updated by the data extracted from the database. This function uses a counter variable to keep track of packages extracted from the database. Callback function is used as a function called inside the interrupt of tkinter. This function checks if the robot is connected. Then it checks if there are any remaining repetitions for the package, and if the number of current boxes is smaller than the target boxes. If so, move function is called. Else, if the number of target boxes is met, or the height is at maximum, the callback database info is called. TK interface is the standard Python interface to the TK GUI toolkit. Both TK and tkinter are available on most Unix platforms as well as Windows systems. The GUI was designed by our team, but the code is auto-generated by Page. Here is the main graphical user interface with every other GUI screen branching out from. Main GUI has the option to log in, log off, and on the right side of it has statistical data displayed in text boxes. This allows the users to track the data concerning orders or their details. There are 3 buttons in the main GUI. One of them is to start the system, the other is to stop the system, and the third is to log in. Then the user is prompted into the second screen where he can log in with user information data. Here, the login function is fetching information from the GUI. If the values are correct and verified, the GUI will execute the function call shown on screen. Then it will start GUI for box insertion. In this box insertion GUI box, information can be added, modified, or deleted.
Results and discussion. All the requirements which are set for the system are met and the functions are fully implemented and operating in the system. As a prototype, the focus was on making it work on a small scale without ignoring the challenges that the system might meet as the scale gets larger. In the development process, our team has used Dobo Magician robot arm. This made the development process easier and faster relative to building our own robotic arm with motors and sensors. We set the limitations on what the project shall do according to the limits of what the Magician robot arm can do. We designed every function without exceeding the limits of the robotic arm. The Domo robot made the development process more convenient. However, it brought some problems to deal with as well. The connection between robot arm and the computer is unfortunately not consistent. The connection between the robot arm system and the computer was indeterministic, and changing the configurations did not help. The team wasn't also able to determine the exact cause of the connectivity error, but an educated guess based on observation has been made that it's from hardware connection issues. Other guesses included the way that the Python commands are queued or the way that tgetter after function works. Based on observation, the team developed a hypothesis that it is because of the hardware of one of the team members' computers. The team stuck with Python as it is the most documented language used for the Dobo API. Besides Dobo connection problems, we have dealt with different challenges in implementation as well. One of them was the graphical user interface package for Python tgetter. Tgetter was operating with a timer, refreshing design interfaces with a certain interval of seconds, and as the interrupt happens, everything within the loops and its implementation was crashing. That limited us and refrained us to use any loops in database implementation and GUI code. We were able to implement our GUI and database regardless of the limitations of the tgetter package. Despite the challenges, our GUIs reflect the values in the database correctly. The robot arm can take the values from GUIs correctly and execute the certain tasks step by step as described in our algorithm. Our GUIs can take user input correctly and save fetch data in the database with success too. Our team decided to use matchsticks to test functions of the system. The pneumatic cycling mechanism at the tip of the arm was able to stabilize the item, and matchsticks are shaped identically in rectangular shape. That was perfect for our testing purposes. These aspects of matchsticks made them fit to be used in our tests. The time required to sort the boxes, the accuracy was out of development process since the project is limited to what Dobo Magician can do and is designed to be a prototype. Before going into the details further, it is important to clarify what the prototype in this context encapsulates. A functional prototype by definition is a prototype that captures most of the functionality and appearance of the final product, but it's made with different techniques and different scale than the final product. The choice was made because the team is well aware that other prototypes or an actual system are either not possible to be made with the material base of the developers or aren't going to be good enough for demonstration. In ideal setup of development process, the motors which are rotating the robot arm should be chosen accordingly for the scale of the project and considering how fast and accurate the system should operate. In our system, we have used already existing electric motors of the robot arm. Therefore, we have ignored aspects of accuracy in sorting and the speed of sorting. However, the results show, as discussed in testing section, that error margin is quite low and the boxes have been sorted in our test without objects being colliding with each other or misplacement of the objects which would make the pile of matchsticks collapse. Functions that were needed to be system specific were made to be especially for the system, and reusing them in other pieces of software is not recommended. The functionality for the database is made specifically for the Psycop G2 adapter, and the functionality for the movement is made specially for the Dobo Magician. In conclusion, the system was implemented correctly and the functions worked as intended with some connectivity faults. The system serves as a proof of concept that such a system can be implemented in an actual warehouse. Such a system is needed because the automatization is already entering a lot of workplaces, and the need for such a system is apparent as the 2020 situation has shown to us.